Hello, everyone. I'm Walter Henderson. I'm a staff member here in the IEN at Georgia Tech, standing in for David Godfrey today. So I want to welcome you to Nano Tech. Thank you for coming. And I want to intro our speaker today. So we're pleased to have Dr. Matt McDowell, who is a Georgia Tech alum, received his bachelor's here in 2008, and went out to Stanford. Worked in the Department of Materials Science there, received his PhD in 2013, and started here in Tech in last fall.
That's right.
2015. Prior to that, he was at Caltech in their chemistry and chemical engineering department. And he's here today to talk to us about, so he has a joint appointment in the School of Materials Science and Engineering and also the School of Mechanical Engineering here at Georgia Tech. And he's here to talk to us today about pathways to improve performance by understanding dynamic materials in electrical systems.
All right.
So thank you.
Thank you. It's a pleasure to be here. I appreciate the invitation to speak at the Nano at Tech seminar. Can everybody hear me pretty well? Mic's on? All right. So today I'll be talking about some of my previous work related to dynamic processes in electrochemical systems and understanding these processes and engineering materials for improved performance. And at the end, I'll briefly mention some of the things that my current group here at Georgia Tech is working on now since I've started in the fall. So in general, kind of as an introduction to electrochemical systems, electrochemical processes and devices are very important for many types of energy conversion and storage. So you guys have probably seen the Tesla Powerwall, right? This is kind of a bid for personalized home energy storage to get off the grid. There's fuel cell vehicles. There's electric vehicles that run on batteries as well. This is a Toyota fuel cell vehicle. They've been pushing these for a long time. There's also devices that can make electrochemical fuels. So basically splitting water is one way to make a fuel. You do this electrochemically to produce hydrogen, right? And so all these different applications are enabled by different types of electrochemical devices. So they're quite important for energy storage and conversion. So if we take a look at what an electrochemical device generically looks like, this is kind of a schematic here. So this is maybe a battery or a fuel cell. You have two electrodes, an anode and a cathode. You have some sort of electrolyte in between. The electrolyte passes ions and not electrons. You then have some external circuit where the electrons pass, right? And so during operation of this electrochemical system, you have ion motion in the electrolyte and electron motion through an external circuit. So on the device scale, these are the types of dynamic processes we're concerned about. But there's different length scales that are important in these devices. So if we zoom in a little bit, look at the surface of one of these electrodes, we may have a bunch of particles that are stacked together in a certain way that are important for device operation. And we've zoomed into the mesoscale now, so we're on a smaller scale bar. But on this scale, there's other things that are important. There's particle-particle interactions that become important. They have to be controlled for good performance. There's also electron and ion transport in this architecture now, between particles and among particles. If we take another level of zoom, go to the nanoscale now, there's different aspects of device performance that we have to care about. So in a battery, for instance, we may have phase transformations that occur in particles. This can cause mechanical degradation, fracture, lots of different dynamic things that happen. We could also have a material synthesis process, such as an electrodeposition, right? When you're growing a new crystal on a surface from the liquid solution. This is another dynamic process. Finally, you can have corrosion and dissolution of a material on the nanoscale, which usually you want to avoid in order to have good and durable performance. So the summary of this slide is that across all these length scales, we have these dynamic things that are happening in these electrochemical systems. And really, to engineer better systems, we have to understand these dynamic processes and control these dynamic processes. So I'll talk about two different research areas today. These are things that I've focused on in the last few years as a PhD student and a postdoc, and I'm continuing to focus on in my faculty position. The first is high-capacity materials for lithium-ion batteries, and the second is developing stable photoelectrodes for electrochemical fuel production. These are semiconductors that absorb light and produce fuels like hydrogen. And the overarching goal is to understand and control the dynamic behavior and interfaces in these systems. And hopefully the last slide was a good introduction about why that's important. All right, so we'll start with batteries. So batteries, of course, everybody knows, lithium-ion batteries have enabled portable electronics. They've enabled the revolution of portable electronics in the last 15, 20 years. Lithium-ion batteries have a very high energy density compared to other types of battery systems like nickel cadmium or nickel oxyhydroxide. But even though they've been very good for iPhones and laptops, moving to new applications like low-cost and long-lasting electric vehicles, which maybe not is this one, but it's a nice picture, we need different types of batteries. So we need batteries that are lighter, smaller, and cheaper. And so this is a big research area, of course. I'm sure many people are familiar with it. But if we take a look at what a battery looks like and try to understand how we can make them smaller, lighter, or cheaper, basically the answer presents itself pretty quickly. So this is a schematic of a battery. We have two different materials that are used as the anode and cathode. And then there's an electrolyte in between. We talked about this before with the ions going through the electrolyte. But the energy limits on this battery are given by this simple formula down here, where the lithium storage capacity times the voltage of the total system is your energy content. And so to increase the total energy content with the same size system, we need to either increase the lithium storage capacity in your materials, or we need to increase the voltage between the materials. And so the materials I'll talk about today are materials with significantly higher lithium storage capacity, which could lead to higher energy density in a full battery system. All right, so one of the materials and one of the primary materials that has received research attention is silicon for lithium-ion batteries. So silicon is a replacement for graphite as the anode material. Graphite holds lithium, and the capacity of graphite is this number here, 372 milliamp hours per gram. That's basically like coulombs, milliamp hours is another way to say that. But silicon, you can see, is almost an order of magnitude, or more than an order of magnitude, almost an order of magnitude higher, right? And so very high capacity. So we know it has a high theoretical capacity, so why don't we use it? The problem is that there's a different reaction mechanism when lithium reacts with silicon compared to when lithium reacts with carbon or graphite. So that's shown here schematically. So lithium actually alloys with silicon. So you take 15 lithium atoms and stick them with 4 silicons, you form a new phase, a new alloy phase, lithium-15 silicon-4. Very lithium-rich, has a very large volume compared to the initial silicon. You can see here, if you start with silicon particles, they'll react with lithium to form larger particles, but they break up into smaller pieces and fracture. There's mechanical degradation that occurs, and this is bad for your battery performance, basically. Your particles can lose electrical contact in your battery electrode, and they become dead weight, basically, and you lose capacity over time. So this is in contrast to graphite, where lithium can actually be inserted directly between the graphene layers in the graphite, and this is a very reversible process. Very small volume change, only about 5%, and so you can insert lithium and remove it over hundreds and hundreds of cycles, and that's why your batteries last a long time in your phones. So these different reaction mechanisms are fundamentally the reason why, even though we know this has a high capacity, we have not been able to use it successfully because of the capacity to decay with cycling. So the goal here, basically, in the research arena on these materials is we know that there's this large capacity, so maybe we can try to understand exactly how the reaction mechanism occurs. And if we can really understand the volume changes, the reaction mechanism, and also the mechanical degradation, the fracture that occurs in these particles, maybe we can engineer them specifically to accommodate this expansion reversibly, expansion and contraction. And if we can do that, maybe we can make a good, long-lasting battery with these materials. But understanding these reaction mechanisms are kind of difficult because conventional electrochemical experiments don't really give you any insight into these mechanisms. So that's what I've focused on in the past, understanding these reaction mechanisms with new techniques. All right, so the main technique, or one of the main techniques that I've used, is called in situ transmission electron microscopy, or TEM. So TEM is a very high-resolution electron microscopy technique where you can image materials at the atomic scale. But in situ means that we're actually doing some sort of reaction inside the microscope, and we can observe it while it happens. So to do that, we use this special sample holder. So the TEMs here at Georgia Tech are downstairs, and they're pretty large. This sample holder is pretty small. This is only about a centimeter wide here, this image. But you can see here, this is a zoomed-in image of this, an optical image. There's 2 probes, one here and one here. So on this sample holder, we have these 2 probes. We can actually put battery materials on these probes. So for instance, we put lithium cobalt oxide, which is a common lithium-containing material, on one probe. And we put silicon, or a silicon nanowire, a nanomaterial, on the other probe. And then inside the microscope, we can actually move these probes together, actually with nanoscale precision, almost a nanometer level precision. And we can contact them. there's an electrolyte in between. So this is a liquid electrolyte. It's an ionic liquid, has a very low vapor pressure, so in a TEM it actually doesn't evaporate. You can also use solid electrolytes, which I've done, and it's very useful. But the electrolyte is key because when you bring these two things together, you've now contacted them, but there's no electrical connection, only an ionic connection. So you apply a bias, and you can cause lithium ions to flow from this electrode through the electrolyte and to react with this silicon nanowire. And you can image the reaction in real time. So it's very similar to a real battery reaction, but you basically build a nanoscale battery cell that you're operating. All right, so here's a video of this process. A little hard to see here because it's dark, but hopefully you'll get the picture. So this is a silicon nanowire. Sorry, this is a nanoparticle. This nanoparticle is attached to a nanowire, kind of shown down here. And you'll see this process. Lithium is going to be reacting with this particle, and you'll see it expand, and something interesting happens at the end. So this is 15 times actual speed. And you'll see this darker core region. See the darker region that's shrinking? That's the crystalline silicon core that's shrinking as the lithium reacts with it. This lighter region around the edge is actually an amorphous lithiated silicon, very highly lithiated, has a larger specific volume, so that's why you see the volume expansion. What happens is at some point towards the end of the reaction is you see this crack initiate, grows across the particle, and the particle breaks into two pieces. So it's pretty cool. This is kind of a real-time demonstration of what might be happening in a real battery electrode that could be leading to capacity decay with cycling. But what you saw there was this process where you have this highly lithiated silicon phase that's amorphous, actually. We know that from the imaging. And there's this sharp reaction front between this phase and the crystalline silicon. And the reaction front moves in concentrically towards the middle of the particle, and eventually we see the fracture occur and the particle break into two. So some questions arise from these types of videos. First of all, why does fracture occur at the surface? We saw the crack initiate at the surface. We need to understand stress evolution to understand how that happens. And then second of all, with these types of images and videos, we can directly correlate the reaction kinetics to the driving force and things like that. So we want to understand the reaction kinetics. So first, I'll just briefly mention this stress evolution and why fracture occurs at the surface. So everyone may not be familiar with mechanical stress analysis. This is actually a calculated plot that shows the hoop stress, mechanical stress, inside this particle in the midst of lithiation. So imagine the particle looks something like this, where there's a silicon core and a lithiated silicon shell, so we're about halfway lithiated here. If we look at the stress across this particle, starting at the middle, going to the surface, we can see that it's fairly large, first of all. So we have gigapascal level hoop stresses. This is much larger than you'd normally find in a chemical reaction. And you can see in the core we have compressed stress, so we have pressure in the core. We move out to the surface, we have this big drop here, which I'll talk about later. But then we actually move towards the surface and we get tension. So there's tension at the surface. So we have these large stresses and we have tension at the surface. And this tension at the surface that arises actually causes the fracture to initiate at the surface. So an interesting thing that I observed along with one of my colleagues, Suk-Woo Lee, this was at Stanford when I did this work, is that there's a strong size dependence to fracture. So particles and pillars, nanostructures of different sizes do or do not fracture depending on their size. So here's just an example plot showing this. So this shows, this is basically, we imaged a bunch of these particles and pillars and determined whether they fractured after lithiation. You can see that particles above about 360 nanometers in diameter fractured 95% of the time or more. But below that, it drops off significantly, almost 0%. So there's this critical size for fracture. It's about 300 nanometers. So below that, you can lithiate these particles. You can have this large volume expansion, and there's no fracture that occurs. This is a really important number for manufacturing real battery electrodes. So nanostructures smaller than this 300 nanometer value should be used in real batteries. So the reason why there's this strong size dependence has to do with the strain energy that's inside these particles. So the strain, if you remember, some of you may have taken some fracture mechanics classes or something like that. The strain energy is what drives the formation of a new crack, right? So the strain energy is just the energy that's contained within the whole structure due to the strain that's there. And there's lots of strain there. But with small particles, there's just not enough material to allow for the strain energy to build up to the point to drive the fracture. So in larger particles, this is the case. So we have strain energy effect that is seen when we use particles of different sizes. All right, so on to the kinetics measurement. So this is another interesting thing. And you'll find out that after we've analyzed the kinetics, actually the stress evolution and these large stresses that exist in these particles actually influence the kinetics strongly as well. But this is an individual particle here we can see, and it's going to become lithiated. I'm just going to show some images here. And what you'll see is we can map out, as a function of time, how big the particle is and how big the crystalline core is. So we started at about 80 nanometers in diameter down here in this particle, or this image here, over this side. After a little bit of time, the particle has begun to be lithiated, and you can see this little darker region. That's the crystalline core. So we can map the outer diameter and the crystalline core as a function of time. After more lithiation, you can see that this initial fast lithiation trajectory slows down quite a bit. So we have fast lithiation, and then the particle the lithiation process stalls over here. And so you can see that in this single particle here as we lithiate. So the reaction slows down. So initially this wasn't too surprising, but upon further analysis, turns out that it was very surprising. So in terms of the detailed kinetics, I asked the question, what kind of kinetics should we expect? So we have these particles. They're reacting with lithium. It's some interfacial type reaction, we think, because we have this reaction front that's moving, the sharp reaction front. So there's basically two different, very simple types of limiting cases that we could expect in terms of the kinetics of this process. The first is if the reaction at the interface, so at this silicon-lithium-silicon interface, was the rate-limiting step. If this is the rate-limiting step, we have short-range interactions that are controlling the kinetics, and the interface itself should move proportionally with time. So it should be a linear shrinking with time. It's actually a little bit faster than this because we have a sphere, but it's very close to linear. For diffusion-limited kinetics, which is the other possible limiting case, or one of the possible limiting cases, we expect that the lithiated thickness should grow with the square root of time. And this is commonly known, the square root of time kinetics for diffusion-limited cases. But in fact, we have neither of these. The data that we observe from lots of different particles slows greater, or the slowing is more dramatic than either one of these. It's more dramatic than linear, of course, because we have this nonlinear effect, but it's also a greater slowing than we'd expect from just a square root of time based kinetics. And I measured many, many particles, 60 to 70 of these particles, and they all showed this slowing effect. So what's happening here? So what we think is happening, is we have this strong effect from the hydrostatic stress that evolves in these particles. So the hydrostatic stress is the pressure. So as we lithiate these particles, I already told you that there are these high stresses that evolve. Near this reaction front, there's actually a very high pressure that evolves, and it changes as a function of extent of lithiation. So this is a little bit complicated, but this is the hydrostatic stress or pressure inside this particle right at this reaction front as we're lithiating it. So as we lithiate, we move this way, and the stress gets more and more negative, so it's higher and higher pressures. And these pressures actually influence the driving force for the reaction. So this is the Gibbs free energy of a generic reaction. The Gibbs free energy, of course, in an electrochemical system has a chemical component and an electrical component. And this is how we usually write it in an electrochemical system. We usually don't write the mechanical component to the Gibbs free energy, but it's there. And the reason we don't usually write it is because it's usually extremely small compared to the chemical driving force or the electrical driving force. But in the case of this extreme volume change reaction, which results in these very large gigapascal level pressures, actually the mechanical driving force for a component of this the Gibbs free energy becomes the same or close to the chemical driving force. And so what we think is happening is basically the particle starts lithiating, and eventually the pressure reaches the point inside the particle that it just stops the process from occurring because it cancels out the chemical driving force for the reaction. So it's a very interesting process, and it wouldn't happen unless we had these extreme volume changes in these particles. So I should mention there's a Ting Zhu here at Georgia Tech very soon after I published this initial paper reported similar observations in nanowires, silicon nanowires under lithiation, and they undergo a very similar lithiation process and similar stress evolution to particles. So it seems like there's good agreement across different types of geometries. And this is an important observation, mainly because you saw how we had this reaction slowing process. So in real batteries, this fundamental process, this fundamental limitation in the kinetics could influence the actual maximum charging rate that you could have in a battery system using these materials. So that's kind of the link towards a real battery system. Okay, so far I've talked about crystalline silicon. So we have this nice crystal. These are all single crystal particles, and they react with this sharp reaction front. But what about amorphous silicon? So many people may know that amorphous silicon is a relatively common material. Silicon is a little bit unique in that way, in that you can easily prepare it in both the amorphous and crystalline states. We've seen for the crystalline phase of silicon, there's a two-phase interface during the reaction. Fracture occurs when the particles are above 300 nanometers. And we also see this slowing in the reaction kinetics. So what about for amorphous silicon? In amorphous silicon, of course, we have a disordered matrix of atoms. There's no atomic lattice. But how does this influence the reaction process? So I have a video here. This is going to be really hard to see. But we will see a little bit of expansion. But the interior will be hard to see. This is a amorphous silicon sphere. It's about 400 or 500 nanometers in diameter. It's attached to a silicon rod here. This is acting as the lithium highway. So this really has no influence on what we're observing. But the lithium travels through this other silicon rod to react with the silicon sphere. So we're concerned with the silicon sphere here. And again, this is 15 times actual speed. So if you could look closely, there's this darker region that shrinks again. It's kind of hard to tell here, but there's this darker region. You can see the expansion. Maybe you saw it. Not that important to see. I have an image here. You can see a little bit more clearly here. This is some spheres in the midst of lithiation. You can see there's this sharp front here between this darker region and this lighter region. So there's less of a contrast here because amorphous materials inside the TEM don't scatter as strongly as crystalline materials. But we can still say that there's a pretty sharp reaction front between this lithiated silicon region and the amorphous pristine silicon region. And in fact, there's been some other work that's shown this is actually an atomically flat reaction front. So the result of this is basically this reaction looks very similar to the crystalline case. And one of the reasons why I bring this up is this was very surprising because from previous electrochemical experiments, actually, the reaction front was not expected to be atomically flat or even flat at all. It was supposed to be very diffuse. But we've observed this very sharp reaction front in these experiments. So the one thing I want to say about amorphous silicon beyond that is I want to contrast the fracture behavior to the crystalline silicon case. So before we saw actually that crystalline silicon particles fracture and there's a critical fracture size. Actually, the particle fracture size is about 200 nanometers. The pillar fracture size or nanopillar fracture size, critical fracture size, is about 300 nanometers. So you can see here's an image of a particle fracturing upon lithiation. So how does this compare to amorphous silicon? So I tested amorphous silicon particles up to 800 nanometers in diameter, and none of them fractured. And actually, since this work, there's been additional experiments showing up to 2 or 3 microns in diameter for amorphous structures. There's no fracture upon lithiation. So amorphous silicon appears to be much more resilient against fracture than crystalline silicon. And so it appears that using amorphous silicon in batteries is probably a good idea, number one. Fundamentally, though, the reason why this is because amorphous silicon expands isotropically during lithiation. So this is something I didn't really talk about, but crystalline silicon undergoes anisotropic expansion. You can kind of see that here. So this is the crystalline silicon core, and this is a halfway lithiated particle. You can see this core is highly faceted, even though the original particle was a sphere. So this faceted core results because lithium actually reacts with different crystal planes of silicon at different rates. And because of that, you have expansion in different directions at different rates. And this causes actually stress concentrations at certain places. And that's one of the main reasons that fracture occurs in these crystalline particles. So that was a very brief explanation of this. There's been a lot of work on understanding the anisotropic expansion of silicon. But it's rather obvious now that amorphous silicon has no underlying lattice, right? It's just an amorphous structure. There's isotropic expansion. And because of that, there's no stress concentrations. And so it's more robust and will not fracture upon lithiation. So it's very promising. These experiments have shown that it's a very promising material. All right, so that's what I'm going to talk about in terms of silicon, understanding silicon reaction with lithium. There's one more slide here. This is just to kind of highlight some of the parallel efforts that have gone into engineering silicon nanostructures and testing them in battery systems and trying to improve their performance. So there's been a lot of work developing engineered nanostructures. So this is actually work from Gleb Yushin's group at Georgia Tech. This is some work from my previous group at Stanford. Here's some citations. But basically, so these studies are dedicated to engineering these nanostructures and testing them in batteries and trying to improve their cycle life. So here's an example of capacity over a number of cycles. You can see that this material here, this engineered nanostructure, this is actually a hollow carbon material with silicon nanoparticles inside, results in very high capacity over 1,000 cycles. So this is much, much better than you would get 10 years ago, where you have maybe a capacity or a cycle life of about 10 cycles. So really improved cycle life. And the main reason is because of these engineered nanostructures that are specifically designed to accommodate this volume expansion and contraction. And I'd like to think that a lot of this work across the world really it's gone hand in hand with some of the fundamental understanding that has also been pretty widespread, some of these studies I just showed, in terms of understanding these reaction mechanisms. And I think that the fundamental understanding has been very important for showing the pathways forward in terms of engineering better nanostructures that can accommodate these changes. So that's been a really nice area of research, I think, for the last 7 or 8 years even. All right, so a little bit more about these battery reactions. So I've been talking about silicon primarily, or only until now. But lithium actually reacts with many, many materials, and there's lots of different options for materials in battery systems. So this is just an example of another material that actually undergoes a different type of reaction with lithium. So this is a TEM image of copper sulfide nanoparticles. So this is a diffraction pattern. These nanoparticles are actually disks, and they're hexagonally shaped. So we're looking down on the face of the disk here. Well, this is actually more like a circle, but they're supposed to be hexagonally shaped. And it has hexagonal symmetry. But these copper sulfide materials undergo what's called a conversion reaction. So instead of an alloying reaction, which we saw before, where lithium simply forms a new phase, a conversion reaction is a little bit more complicated. So here's the chemical reaction, or the electrochemical reaction, I should say, of lithium with copper sulfide. So you start with copper sulfide, you add lithium ions and electrons to reduce the material, and you end up with two different phases. You end up with lithium sulfide, which is the lithium reacted with the sulfur, and then you also have copper metal. So this is more complicated, and the question is, we have these particles. We know what should happen electrochemically, but we don't know how the morphology should change, and we don't know how the volume should change, because this final mixture of two phases could take any number of forms. So studying this type of reaction is also quite important. So this is what this looks like, actually. So these are two different copper sulfide particles, and they're sitting on a carbon support here. We're looking along the edge of one of these particles, so you can see actually the lattice fringes here. It's a very high-resolution image. This is the Fourier transform of this image. So these spots here correspond to these lattice planes, and these lattice planes correspond to these spots here. So we can determine that this is copper sulfide and it has the correct lattice spacing and all that. So this is before reaction. So in this process, we can image these particles right before reaction and right after reaction. So after reaction, they look like this. So before, we have these nice lattice fringes, and right after, it's changed quite a bit. We still have this particle down here, you can see. We still have these lattice fringes, see, before and after. But now we have this little hat, right? This guy's wearing a hat now. And what's this? So this is actually the copper. This darker region is the copper metal. This lighter region down here is actually the lithium sulfide. So this is kind of subtly very interesting. Before we had this copper sulfide particle, after we've ejected the copper metal to form a new copper particle, nanoparticle, and now we have a lithium sulfide particle that is in the exact same location with almost the exact same lattice spacing as the initial copper sulfide. So we retain the morphology even though we undergo this rather dramatic transformation. So that was interesting when we discovered this. So why does this happen? So if we look at the atomic level structures of these two materials, copper sulfide and lithium sulfide, we can get a good idea of why this retained morphology occurs. So here's copper sulfide, high resolution image. This is a fast Fourier transform. Same thing for lithium sulfide. You can't really tell much from these images. They look pretty good, though, I must say. But let's look at a schematic to help us understand what's going on here. So this is if you take this image, actually, you can basically map it out onto this schematic. So this shows the sulfur atoms in the atomic structure in the yellow, and then the copper atoms, which are dispersed in a rather complex manner in this copper sulfide material. The important part here is if we look at lithium sulfide, the sulfur atoms are in almost exactly the same lattice points. The spacing between the sulfur layers is almost the same, only about 2% different. And so basically, the sulfur sublattice in these two materials is almost exactly the same. So what happens is when we insert lithium into the copper sulfide, the lithium comes in. The copper can actually diffuse very quickly. This is a material known for that. And the copper actually diffuses out of the material and forms a new copper metal particle on the surface. And lithium basically just replaces it in the lattice. And so this is kind of like a cation exchange process almost, where this usually happens in a liquid environment, but here it's in solid state. And so we have this interesting, we basically retain the particle morphology during this exchange process. And this is just very brief here, but we can also image this process while it happens in slightly larger particles. So this is a copper sulfide particle here before the reaction. This is lithium, the same particle, lithium sulfide, after the reaction. But we can color code the two different phases as the reaction's occurring. So in red, we have copper sulfide to start with. As we start the reaction, we can see that some blue phase forms at the left side. That's the lithium sulfide phase. And as we go across, the lithium sulfide phase grows across the material and eventually converts completely to lithium sulfide. So this is different than the images before. This is actually a high-resolution atomic level image showing a reaction that's occurring across this single particle. So this is actually kind of difficult to get this data, so I'm pretty proud of it. All right, so one more slide here. So this is pretty cool. So I've showed you what happens when a single copper sulfide particle reacts with lithium. We have this transformation in the lattice. The copper gets kicked out to form this new particle. But something really interesting is what happens when you have a bunch of these copper sulfide particles all touching each other. So that's what's happening here. There's probably 100 or 200 copper sulfide particles in this region here, and it's kind of thick. That's why you see it's dark. You can't really see through it with the TEM. But what's happening is they're all reacting with lithium. And the copper, I mentioned before, is a very fast diffuser in this system, just like lithium, actually. But what's happening is it's more energetically favorable for the copper to diffuse together from all these particles and diffuse through the particles and then form a copper metal dendrite that grows. That's more energetically favorable than simply forming a bunch of little copper particles. So what we see, actually, is this large copper dendrite that grows during the lithiation process. So this is actually, this is obviously dynamic. We're seeing this copper metal dendrite grow out of this solid material. So this is really weird to see the first time I saw it. I mean, unexpected, definitely. But it's only enabled by this interesting structural change and also the very high diffusivities of copper in this material. So it would be interesting to compare this to the reaction of copper sulfide with other alkali metals like sodium or potassium to see if the same kinetics and the same morphology changes hold. All right. OK, so in the last 15 minutes or so, I'm going to switch gears a little bit, no longer talking about batteries, but talking about a different electrochemical system. And this is materials for solar fuels. So solar fuels fundamentally means we're going to absorb sunlight and create storable fuels, either hydrogen or hydrocarbons. One way to do this is actually to use semiconductors, which we know can absorb sunlight, like in a solar cell. But instead of using them in a solar cell, use the semiconductors to do electrochemistry. So basically use semiconductors that absorb light and split water. So the idea here is that theoretically you could make a simple and cheap solar to fuels device using semiconductors that are doing electrochemistry. So to split water, this is the simple reaction, of course, you all know this. You need a Gibbs free energy of 1.23 electron volts to split water. So this is rather high, especially for a semiconductor system. I mean, most solar cells, single solar cells will produce between 500 to 700 millivolts. And so here we have 1.23 volts that's required. So this complicates the situation a little bit. And I'll just mention hydrogen is a useful fuel because it can be used directly in fuel cells, as many of you know, of course. But it can also be used to further process carbon monoxide into storable fuels, liquid fuels. And so this could be a nice feedstock for renewable fuels. That's why hydrogen is of interest. But this is a schematic of a solar fuels device. So this is an original design that was invented at Caltech probably about a decade ago now. But this basically contains two different semiconductor materials. And you take this whole device and you actually dunk it in water. That's how it operates. So the semiconductors are labeled photoanode and photocathode. The photoanode is a larger band gap semiconductor, so it can absorb UV light or near UV light. The photocathode is a smaller band gap semiconductor. You then have this membrane separator that's quite important actually in between. So it separates the products and it also allows for ion transport. But the important reactions that are occurring is you're absorbing light in the photoanode semiconductor. And so you have photogenerated holes. So you have excited holes, charge carriers, that move to the surface of the semiconductor. And they react with water actually. The holes react with water to oxidize water. And they form oxygen. So you have the oxygen evolution reaction happening here. In the bottom semiconductor, you have the hydrogen evolution reaction. So the photogenerated electrons move to the surface and they react with water to form hydrogen. And so this is a totally contained full water splitting process where on the top electrode you're forming you're forming oxygen, you're evolving oxygen. And the bottom electrode, you're evolving hydrogen. And so there's lots of details here. We won't go into all the details, but that's the important things that you need to know regarding the whole device. The really big problem with these devices and with this whole field actually is that basically all semiconductors or many semiconductors are unstable in aqueous environments. And this is actually exacerbated when you shine light on it because often the photogenerated carriers like the holes have a very high energy and they can actually corrode your material instead of doing the electrochemistry you want them to do. And so photoanodes, where the water oxidation happens, they operate at a high potential, and they are especially susceptible to photocorrosion because these photogenerated holes can corrode the material itself. So this is an example of what photocorrosion looks like. This is a photocurrent stability test. So this is a semiconductor material that's dunked in actually a slightly basic or pretty basic solution, and light is shown on it, and we're measuring the current that's evolved during water oxidation as a function of time. And you can see first we start with about 1.4 milliamps per centimeter squared. And over the course of 15 minutes, we drop off to a very low value. And so our performance is decreasing. This is because the surface of the material is corroding away. And we can verify that by looking at before and after images of this thin semiconductor film. This is bismuth vanadate, actually. It's a type of oxide semiconductor. So this is before, and this is after. We can see actually that we've lost the material here. So this is an example of the photocorrosion process. So the first thought would be, okay, so we have these semiconductors. We want to protect them underwater. We want them to still retain their functionality. How do we do that? Well, the first thought would be, I guess, to try to put something else on top of your semiconductor, right, to protect it from corrosion. That's rather an obvious thought, actually. I mean, people have been thinking about that for a long time, maybe 40 years. But the problem is it's actually kind of difficult because there's a lot of requirements for these protection layers. So they have to be resistant to corrosion, first of all. They have to be transparent. They have to let light through. They also have to be conductive to photogenerated carriers, and this can be the hard one because many materials that are resistant to corrosion and transparent are wide band gap oxides that are not conductive. They also have to be catalytic for the oxygen evolution reaction or the hydrogen evolution reaction, depending on which one you're doing. And so these are a lot of different requirements. And so there's some trade-offs, right? So the insulating oxides can be corrosion resistant and transparent, but they're generally not conductive or electrocatalytic. So that's a problem. So basically, we need to find the right material and the right fabrication process. So this is actually something that I started working on as a postdoc in conjunction with a number of other colleagues. This is at Caltech and the Joint Center for Artificial Photosynthesis there. And so we basically developed a number of different ways to deposit very thin films and thicker films designed to protect these semiconductors from photocorrosion. This is one example. So this is using ultra-thin ALD protection layers. This is a schematic. So this is the green here is the semiconductor. It's bismuth vanadate. And I developed this dual ultra-thin coating, dual layer coating of titanium oxide, which is deposited with atomic layer deposition, and then also nickel, which is catalytic. So we kind of taking apart the two functionalities. This was pretty promising. This coating allowed for an increase in stability time from about 10 minutes to 2 hours. But the electronic conduction process through these very thin layers is most likely a tunneling process. So that's why we're able to conduct electrons to oxidize the water. But the problem with these very thin materials, these thin coatings, is that there's always defects in pinholes. And it's very difficult to get sustained stability over 10, 20, 100, 1,000 hours with these very thin coatings. So moving towards thicker coatings that are very carefully processed is necessary. And so just briefly here, there are two different types of coatings that I've worked on, and in conjunction with some other colleagues as well. Two different oxides, both titanium dioxide and nickel oxide, that have shown very good performance and as protective layers for photoelectrodes for these water splitting devices. Basically have improved the stability of these electrodes now to unprecedented levels. And so this has been really an important breakthrough basically in this field. And it's not just me that's done it. It's been probably 10 to 15 grad students and postdocs at Caltech who have been working on this. So I'll first talk about titanium dioxide. So basically, we're going to use silicon now as our semiconductor, N-type silicon. This is a very easy material to work with, as probably many of you know. And we deposit 100 nanometers of amorphous titanium dioxide on the surface with atomic layer deposition, and then a very thin nickel layer as the catalyst layer. This is kind of similar to what I just showed, except this is much thicker titanium dioxide, and so we don't expect that tunneling will have any kind of effect here, right? We have to have some sort of conductivity through the TiO2 for the photogenerated characters other than tunneling. What we see is when we test these devices, so this is an electrochemical test of this electrode that's built up with this multi-layer stack here. The details here aren't important, but in the dark you see this is a standard catalytic electrode. You see a catalytic turn-on, a current turn-on at some point. This is the silicon electrode over here, and we can see that we do have photocurrent that flows. If anybody's familiar with photovoltaic curves, IV curves, we analyze these in basically the same way, these photoelectrodes. Won't get into the details there, though. What this plot shows is we do have a catalytic current that's due to flowing. We have this flowing, and this is surprising initially because we actually expected that this amorphous titanium dioxide would completely be a blocking layer to the holes that are trying to flow through it. But in fact, we do get flow of current, and we do get pretty good performance, actually. So another aspect of this is that the stability is very long. So this is stability of these photoelectrodes that are oxidizing water in pH 14 KOH. And you can see here that we're showing the photocurrent over 100 hours, and it's fairly stable. These have been further tested over now to many hundreds of hours without any kind of degradation. So it's promising as a protective layer, and it still allows for this current to flow, which was initially quite puzzling. So to kind of just briefly mention some of the properties of this material. So this is a TEM image showing the amorphous TiO2 layer on top of silicon with a thin nickel layer on top, which again is the catalytic layer. And this is a high-resolution image of the interface here, the silicon TiO2 interface. There's always some silicon oxide at this interface, which we actually think plays a role in developing the photovoltage. But the interesting thing with this material is that we're actually, I wanted to show this because it's very complicated. This is actually the band diagram that's been mapped out using XPS by my colleague here, Shu Hu. And basically, his set of experiments allowed us to really understand how current was flowing through these materials by mapping out the band diagram. But I'm going to show a little simplified version, right, because the other one was way too complicated. So here we're looking at the N-type silicon. This is the material that's actually absorbing the light, and the photogenerated holes are being generated there. So this TiO2 layer sits right across the interface from silicon. And the point is we want to get holes from the valence band of silicon through the TiO2 to the nickel so that they can oxidize water. So the question is, how is this happening? This question is not completely resolved, unfortunately, but there's a few options. The first option is that basically the holes can recombine with electrons in the TiO2 conduction band that are coming from the water oxidation process. That's one option. A second option is actually that the holes move through these mid-gap states in the TiO2. This is a controversial option, I would say, and there are ongoing experiments to determine whether this is actually happening. If it is happening, it's quite exciting because it could be a way that we could modify the band structure of TiO2 to allow for different types of different energies of holes and electrons to pass through. But this is an ongoing process. But fundamentally, we do have conduction through the TiO2, and we think it's either through this conduction band mechanism or through a mid-gap states mechanism. We have measured the mid-gap states with XPS and other techniques. They are there, and they're at this energy, and there's a significant, they're about 10 to the 20 per centimeter cubed. So it's a pretty high density of mid-gap states. But the actual conduction mechanism has yet to be resolved. All right, so nickel oxide is another protection layer. So TiO2 has been studied for a few years now, and we're still trying to understand exactly how the conduction is happening. Nickel oxide happens to be actually better than TiO2 in terms of performance. This was only discovered recently. But one of the reasons why is because its properties are exactly what you want for these protection materials. First of all, it's transparent, it has a high band gap. It's also very stable in alkaline environments, even more stable than titanium oxide in some cases. It's also p-type, and so there's no question about how the holes are being transported through the material. And finally, it's catalytic for OER. So all these things together make it a very good protection layer. So here's the stability of a silicon electrode that's been protected with nickel oxide. And you can see here that we're going to more than 1,000 hours with very little current decay. And so that's very promising performance. People at Caltech are now making full water splitting devices from these, utilizing these protective layers basically for performance that's basically never been seen before. So it's pretty exciting. All right, so I think I have this slide and then one more slide just to end up. Make sure I have enough time here. You have just a few more minutes. So just in summary, I talked about two different systems, right? We had battery systems, and I talked a lot about how fundamental understanding of these reaction mechanisms and mechanical degradation has really actually created direct links between engineering nanostructures for better performance. And in a lot of ways, we wouldn't have been able to do that without these fundamental studies. And then also talked about water splitting and solar-driven water splitting and how we can tailor interfaces in these materials and these devices for dramatically improved stability and performance. So examples of two different systems. So for the last slide, I'll just talk a little bit about what my group here is working on. So actually, my two graduate students are here in the room. My group here at Georgia Tech is focused on bridging material synthesis, in situ characterization, and device performance in these electrochemical systems. And as you can probably tell, this follows directly from my previous work. We're interested in a few different projects right now. We've started a project on tailoring interfaces in solid-state electrochemical systems. And a lot of times, interfaces in solid-state systems like batteries are reactive and have to be tailored and controlled for greater stability. I'm also quite interested in, we're working on multi-scale in situ probes to understand electrochemical reactions and chemomechanics and battery materials. So this goes beyond in situ TEM, which we're still doing, but trying to correlate phase transformations and structural changes across length scales in these systems is quite important. I think it's really the next frontier. And finally, we're working on a project related to ionic materials for resistive switching. And this is kind of a esoteric application when it comes to electrochemistry, but it's actually for non-volatile switching, and non-volatile memories and resistive switching. All right, so I'd like to thank everybody for your attention. These are some of my previous coworkers and advisors, my current group here at Georgia Tech, and previous funding sources, and also a little bit of current funding. So thank you very much for your attention, and I'll take any questions if there are any.
We have time for a few questions.
It's a really nice talk.
Thank you.
The copper sulfide lithium system, it should not be reversible. It should have hysteresis.
Yeah, large hysteresis. Yeah, probably about a 1.5 volt hysteresis. But interestingly, it has a lower hysteresis than other conversion reactions. And it's thought to be due to the fact that copper has a very high diffusivity in the material.
Yes, but it's driven by the disproportionation reaction.
That's right. That's right. Yeah.
So wouldn't you do better if you actually had a mixed redox states where you would not go to an electrically neutral metal, like maybe manganese, maybe
like some sort of oxidized metal.
2-3 valencies rather than to go to 0.
Yeah. Yeah. The question or the comment is that perhaps it could be more reversible to go to an oxidized metal in terms of the conversion reaction. Yeah, I think you're right about that. Manganese could potentially be useful. I'm sure people have studied manganese oxide or manganese sulfide as a conversion reaction. Yeah. The problem with that is you'd have less capacity available because the capacity is driven by the change in the oxidation state. The more lithium you can put in, right? And so you'd be trading off maybe more reversibility for less capacity.
And if I may, mercury may behave the same way as the copper.
Mercury? Ah, yeah, maybe so. I don't know if I want that in my battery, though.
Well, there are mercury batteries. And the second question is on this titanium silicon system.
Mm-hmm.
You have an intermetallic stage. The silicon forms a silicon monoxide.
At the interface?
Yeah, at the interface, and titanium monoxide.
Mm.
So you actually have a surface state
Mm-hmm.
which is a mix of
Mm-hmm.
surface state.
Mm-hmm. Yeah, that's a good comment. Yeah, definitely. Actually, my colleagues have done some XPS on that interface, careful work to show that there definitely is a mixed silicon titanium oxide. I don't know about the monoxide, but if that's been shown previously, yeah.
It is
Maybe you showed it.
It's actually brown.
Okay.
Yeah,
Okay.
spectrum. Yeah.
Okay, great. Thank you.
So, what is decided the critical fracture size of the silicon nanoparticles in the batteries?
What is the fracture size?
Yeah, what factors?
What factors? So it's driven by the fundamental nature of the volume expansion in the reaction itself. So in the crystalline silicon case, you had this sharp reaction front, and you actually have anisotropic expansion. So you have more expansion in certain directions that's driven by the crystallinity of the lattice. And because of that, you have stress concentrations that are much higher, and so you have a small critical fracture size. In the amorphous case, the critical fracture size is much larger because you basically have lower stresses that evolve, and that's just because of the way that the reaction works.
So does that mean amorphous silicon is more popular than crystalline silicon?
Yeah, I mean, amorphous silicon should be more popular. So I think in terms of previous research that's been done, most people have looked at crystalline silicon just because it's easier to make usually in nanostructure form. But in terms of actual applications, I think that manufacturers that are looking at silicon in their batteries are definitely considering amorphous silicon because of its greater reversibility.
And I still have another question. That is the fracture is mainly due to the alloying reaction between the silicon and the lithium. Is that possible another research direction to replace lithium with other kind of metal material for battery application?
Like sodium or something? Yeah, that's definitely a large research area. Each different alkali ion that you use has its own serious challenges beyond just fracture, right? So in this lithium silicon case, we've gone from many choices of materials to silicon, and we've narrowed in on this one of these last few problems, which is the fracture mechanical degradation problem. But if you go to sodium or magnesium ions as your active ion in your battery, these are very young fields. Actually, they've only started in the last few years, and there are many issues associated with that. But there's a large research area. Many people are looking into that. Lots of work to be done in that area. So.
Okay,
Okay, one more in the back. Who's asking?
I was curious about when you delithiate, so if you start from a crystalline silicon
Mm-hmm.
lithiate and then delithiate it, what does the silicon look like afterwards?
Yeah, that's a great question. So I didn't talk about that at all, I guess. So it turns out that if you delithiate silicon, no matter if it starts as amorphous silicon or crystalline silicon, when you delithiate it, it remains amorphous. Yeah, so it always, through cycling, it remains amorphous. So starting with crystalline silicon is not really a good idea because it turns amorphous anyway, and it stays amorphous. But it turns the way that people have studied this material in the past is that they've pretty much always used crystalline silicon. And in the last few years, this has changed, as this research has come out and as people have seen this. But definitely, amorphous is more reversible, and also it retains that structure with cycling. So.
I just want to know the lithiation process is affected by electrical field and the direction of your the lithium-ion flux.
Yeah. So the electric field, are you kind of asking about the specifics of the in situ experiment or just in general?
Because what you show in the picture is quite uniform in the isotopic amount on all directions, but you're doing this in the electrical field or you're without any electric field?
Yeah, so in a normal battery, the electric field is generally pretty uniform because you have these parallel plates and you have a large surface area. In my in situ experiments, the electric field is highly concentrated because you have maybe a single nanowire and a counter electrode and a small gap. And so you can have very high electric fields. But in general, one of the important things about these in situ experiments is that you always have to do some ex situ experiments that maybe not will tell you the same things, but they will give you some idea that what you're seeing in situ is actually relatable to a real battery. So in all these cases, we did ex situ experiments to look at before and after transformations to ensure that what we were seeing was what would happen or what is similar to what happens in a real battery system. So.
But in your case, it's more like parallel electrode or like micro electrode.
Yeah. So it is a bit different than a real battery system, but it's the only way that you can really do it inside a TEM. So.
Let me take one more question. I guess Chris, your hand is up.
Okay. Well, in situ experiment, I'm just wondering, you probably mentioned that how do you initialize the reaction?
How do you initialize it? Yeah, so you apply a voltage.
You apply the voltage?
Yeah. So just like a real battery, you have a counter electrode material, an active electrode material. You breathe them together, there's an electrolyte in between. And then inside the TEM, you apply a voltage. The special sample holder allows you to apply a voltage.
For the movie dynamic, is that the possibility due to the electron?
The TEM beam? Yeah. So there are beam effects, but they don't cause the lithiation. The beam effects can be controlled. If you're under high magnification during these experiments, you can actually see the material changing. The main beam effects are that the lithium-containing materials inside the TEM are kind of unstable. So if you zoom in, the lithium actually evaporates. But basically all the images I showed with the silicon was at low magnification. And if you do the experiment with the beam blanked, you get the exact same transformations. So that's a good way to test that. So.
Well, let's thank again